Alrighty, in this video we are going to be talking about optimization. We're going to do one problem. We're going to do it the pre-calculus way, aka the Math 2 way, and then we're going to talk about the optimization way, aka using the calculus way. Alright, so we have a rectangular garden that is to be enclosed using the wall of the building as one side. So let's say this is our building, and we have our garden right here. And we have 60 feet of fencing. We want to find the length and the width that will give us the maximum area. Well, I know that this is going to be X, this is going to be Y, this is going to be Y. And let's say that I have 60 feet of fencing. So I know that if my perimeter is X plus 2Y, one of my equations I'm going to be using is 60 is equal to X plus 2Y. We want to maximize our area. So remember that if I want to maximize my area, I want my area, aka the rectangle, to be X times Y. Now in Math 2, whenever we did something like this, we did substitution since we want one variable. So we're going to relate this equation and this equation by using one variable. And what I'm going to do is go ahead and subtract 2y is equal to x so that I have one variable right there. Using substitution, I'm going to get 60 minus 2y and then y. So now I have one variable. Great. I'm going to simplify that. So I have negative 2y squared plus 60y. Great. All right, so at this point, because I want to maximize this and because this is a parabola, what I can do is think about, the axis of symmetry, because remember that the axis of symmetry is going to give us our maximum. And thinking back about our Math 2 skills, our axis of symmetry is negative b over 2a. So we're going to be using that with our equation. Negative b is going to give us negative 60. 2a is going to be 2 times negative 2. So negative 60 over negative 4 is 15. So this tells me that my y value is 15. And if my y value is 15, this is going to tell me if I were to substitute n15 here, I'm going to get 60 minus 30 or 30 as my x value. So this tells me that my length needs to be 30 and my width needs to be 15 on both sides. And this is going to tell me my maximum area if I just multiply it out. If I multiply it out, 30 times 15 is going to give us 450 feet. Yay! Number 2 is essentially the same thing, except this time I have 2,000 feet of fencing. So instead of 60, I have 2,000. Same thing. Now, doing this using calculus, what we're going to be doing is following a couple of steps. Whenever we're solving optimization problems, we want to really understand the problem, read the problem carefully, and understand what's going on. So ask yourself, what's the unknown? What are the given quantities? What are the given conditions? We might want to draw a diagram. We probably will introduce some variables. We're going to write a primary equation for the quantity to be optimized. We might be given a secondary equation if needed, so that we have one single independent variable. So notice how here on number 1, we kind of had two equations. We had p is equal to x plus 2y, and we had a is equal to x times y. Our primary equation would be the equation that we want to find our maximum of, aka this right here. So this equation right here was called our secondary equation because we needed this to make sure that we had one variable, in this case, y. We want to determine our feasible domain. And then we are going to solve and interpret our answer in context. Obviously, we want to make sure that our answer makes sense. So what we're going to do is look at number 1 again, but this time in a calculus way. I'm going to go ahead and draw my little garden. We have X, we have Y, and we have Y. Once again, we have 60 feet of fencing, so I have an equation. P is equal to X plus 2Y. 60 is equal to X plus 2Y. And we have the maximum area that we need to find. So that's A is equal to X times Y. Once again, because we are maximizing area, and since we're doing this in terms of, let's say, the calculus way, this means that we're going to have to take the derivative, find the critical points, and see where my derivative changes from positive to negative because it's asking us for the maximum area. All right, because that's happening, this tells me that this right here is going to be my primary equation since I want to find the maximum area. And this right here is called my secondary equation because that's going to help us put my primary equation into one single variable. All right, so doing that, I am going to once again solve for X. And then I'm going to substitute that into my X right here so that I have one independent variable. I'm going to go ahead and distribute the Y. And then at this point, the non-calculus way, we would have used axis of symmetry. But using calculus, what we're going to do is go ahead and take the derivative of this with respect to Y. That's going to give me that. So this is equal to 0. If I solve this, I'm going to get Y is equal to 15, aka my critical point. Now, our derivative is easy peasy lemon squeezy because it's just a linear function with a negative slope. So my function should look like that, where anything to the left of 15 is positive and anything to the right of 15 is negative. Based off of that, because I have a sign change from positive to negative at 15, this tells me that 15, Y is equal to 15 is going to give us our maximum area. And once again, to find X, we're just going to plug in 15 into my equation, my secondary equation, and see that X is 30. And then, once again, if I multiply, this is going to give me 450 square feet. All right, so that was a little introduction to optimization, an easy peasy lemon squeezy problem. Try 2 on your own, but in the next video, we are going to look at some more complicated problems. Let's say number 3, 4, 5, 6. We'll see where that takes us, but we'll do those in the next video.